Hello everyone, and welcome to the first of 5 videos to help us review for the final. So these videos will have open-ended solutions, even though the test itself is actually multiple choice. Part of the questions that you're going to get on the final will be multiple choice numerical solutions that you will have to show your work for. So this is kind of what I'm preparing for here. So we're just going to jump right in with the first section, which is going to be momentum. An egg drop capsule is dropped from the balcony by the Black Box Theater. By the time it reaches the ground, it is traveling at a velocity of 7.5 meters per second and has a mass of 100 grams. It has the mass of 100 grams before you drop it also. What is the impulse exerted on the capsule by the Earth? If an egg breaks when a force of 36 newtons is applied, how much time should it take to stop the egg so that it does not break? So let's get started. So this is a momentum impulse problem. So there are many different ways to solve this type of problem. We'll go through a couple of them here. You can pick your favorite. So first of all, if you check your equation sheet, the equation for impulse, delta P is equal to, I don't know why it's red, F delta T, which is equal to M delta V. So, and this is all impulse J. So any of these equations will be suitable for solving it. Because we don't know the amount of time it spends in the air, this one is out. But we do know the mass, and we do know the velocity, and the change of velocity really, because we know that it was started from rest when we dropped it. So the initial velocity is 0, which means that the initial velocity is 0, the final velocity is 7.5, and the mass is 100 grams or 0.1 kilograms. So we can use this part of the equation to calculate the impulse. And the reason that we say we can call this the impulse of the Earth is because when you drop it, the Earth is the thing outside the system exerting the force on the capsule. So simply put, J is equal to M delta V. Now once again, M has to be in kilograms, not in grams, so that's moving the decimal point over 3 spaces to get to kilograms. So it's 0.1 kilograms times delta V, which in this case, V final is going to be, let's have V final positive 7.5. So you got your V final, 7.5 meters per second, minus V initial, which is 0 meters per second, which gives us a impulse of 0.75 Newton seconds is the units for impulse. Probably because the thing is so light, it doesn't actually have that much of an impulse. So that's A, simple enough. For B, if an egg breaks when a force of 36 newtons is applied, how much time would it take to stop the egg so that it does not break? Both of these problems are very simple. So now we're done using M delta V. We will now use F delta T for this part. So we know this was the impulse for while it's dropping. So to calculate the impulse for when it's stopping will actually be very similar. So J, or delta P, change in momentum, for when it's stopping is equal to, once again we'll use M delta V, and we know this time that delta V is going to be initially from 7.5 meters per second to 0, because it's stopping when it hits the ground. So we have the same equation, 0.1 kilograms times, this time we have 0 meters per second as our final velocity, minus 7.5 meters per second as our initial velocity, which will once again give us this time a negative 7.75 Newton seconds. So that is our delta P, right? That's our impulse for when it's stopping. So this is the impulse for falling. This is the impulse for stopping when it hits the ground. Notice it's the same because it's happening, it's all happening to the same thing, so it gets to a certain speed and then loses that speed once it, or velocity, I should say, once it hits the ground. The difference here, though, is the amount of time it took for this to all happen. So, as we said, the egg will break if a force of 36 newtons is applied. So now we're going to apply this equation, this part of the equation. So we have our delta P, which is negative 0.75 newton seconds. That is equal to F delta T. So in this case, F is 36 newtons. And delta T is what we're solving for. So we'll divide both sides by 36. It's going to be a very small time indeed. Notice that if you divide newton seconds divided by newtons, you end up with just seconds. So this is 0.75 newton seconds divided by 36 newtons, which gives us a velocity, this gives us a delta T of about 0.021 seconds. Not very long at all. Alright, so there you go. That is using impulse, both parts of the impulse equation to solve for various physical quantities involving impulse and momentum. Let's move on to the next momentum question. So two identical bullets are fired at a block of wood, or each fired at a block of wood. One bullet is a rubber bullet that bounces after it collides with something. The other is a standard bullet. These bullets are fired at identical blocks of wood. The bullets have a mass of 20 grams each. The wood block has a mass of 500 grams, and the initial velocity of the bullets is 300 meters per second. It can be sort of assumed that the v initial for the block is equal to 0. They're stationary, presumably. So after the bullet strikes the blocks, the regular bullet embeds in the block and starts sliding, while the rubber bullet bounces off the block in the opposite direction at a velocity of 100 meters per second. What is the final velocity of the block in each experiment? So what we have essentially, so we have the before and after for each experiment. The before is going to be each bullet is fired at a block of wood. The velocity for each bullet is 300 meters per second. That's 300 meters per second. The mass of the bullet is going to be 20 grams, so that's 0.02 kilograms. And the mass of the block is 500 grams, so that's 0.5 kilograms. Obviously V is 0 for the block. So this is going to be essentially the same case for both the bullets. I'm not going to draw the second one. But this gives us two different outcomes depending on the rubber bullet or the regular bullet. So for the regular, the block and the bullet embeds in the block, basically. And the two start sliding with some velocity v final that we don't know. The rubber one bounces off the block, which also starts moving with some velocity v final that we don't know, and we happen to know that the bullet bounces off at a velocity of 100 meters per second. So about a third of the velocity that was moving initially with. And so the question here is, what are the two v finals for each experiment? So, you are watching my recording thing. Why would we do that? So let's start with, we started with our diagram, our picture. The next thing to do would be to draw a bar chart to match the scenario. I don't think we need, I think we have all the information in our picture, so I'm going to slide this down here. So for the bar chart, we need our system in each case. We'll have to have two bar charts, one for the rubber bullet and one for the regular bullet. This bar chart will then help us determine what equation we can use to solve each problem. Okay, there's our bar charts all set up. So the system I'm going for both is going to be the bullet and the block, which I'm going to call wood because they both start with B and I need to differentiate them somehow. So we're going to call this wood. Alright, so the system is the bullet and the wood. So we have our initial momentum bullet, and initial momentum for the wood, and we'll call this the rubber. This will be the rubber bullet. And this will be the regular. Sorry for my handwriting. So, and then here's our delta P, and then we have the final for the bullet and the P final for the wood, and then we're going to end up with the same thing here. There we go. And now we have our bars. So for the bars, in both cases, the bullet has all the momentum and the wood has none. So we're going to start off with a bunch of momentum here. And by a bunch, I mean like 2-3 bars. And we'll do the same here. Okay, this is where we're going to split off. So in both cases, because the bullet and the block are both in the system, and we're ignoring the fact that there's going to be friction between we're going to be ignoring the fact that there's friction between the wood and the ground, so we don't care how far it's traveled, although that would be a question for like an AP class. We do care about how fast it's moving right after they hit. So the bullet and the wood are both in the system, so the wood has 0 momentum. There is no change in momentum. There's no forces outside the system that are interacting with either one. And then in the final case, for the rubber bullet, the bullet itself travels in the opposite direction at 100 meters per second. So we'll call that a third of the initial, so it'll bounce off with 1 block, and that means that our final momentum for the wood has to be 4 blocks. We know that the total momentum here has to equal the total momentum here, right? This plus this is equal to this plus this. So if there's 3 blocks here, and it needs to be equal to -1 plus 4, which will give us 3. So these both sides are equal. Here, because this is the regular bullet, because they're stuck together, they both start traveling together with the same velocity, but because the bullet has less mass, much less mass, then the bullet is going to technically have less momentum. Not technically, actually. Sorry, Matt. Definitely will have less momentum than the block. Obviously not half the momentum, because it is a much smaller fraction of the mass, but you get the idea. So just that the bullet has less mass than the wood block. Alright, so now that we have this, we can write out our equation for each one. So let's do the rubber bullet first, sort of all the way through, and then we'll do the regular one all the way through. So we have P initial for the bullet plus 0, so we can ignore that, is equal to the P final for the bullet plus the P final for the wood. Notice I made this positive, not negative. We can do that. Just be careful that you don't double negative up here when you start putting in the velocity. So if we make this negative, then we're just going to put in the speed, basically. We're going to put in 100 meters per second, and that will account for the fact that it's in the opposite direction. So now our equation. So the equation for momentum is mass times velocity. So this is mass of the bullet, v initial bullet. And then for the block, we have negative mass bullet, v final bullet, plus mass wood v final wood. Important for this to be negative, don't forget that. Then we can now, sorry, I'm going to slide this down a little bit. We can start plugging in values and calculating our solution. So the mass of the bullet we said was 0.02 kilograms, and the initial velocity of the bullet was 300 meters per second. And once again, we have the mass of the bullet, which is 0.02 kilograms, times the final velocity, which is 100 meters per second. Again, I didn't put this in as negative because we counted for the negative sign here, plus the mass of the wood, which was 0.5 kilograms, times the final velocity, which is what we're trying to calculate. Okay, so now by the magic of some video editing, I'm going to do the algebra very fast and show you how we get the solution for V final. And there we go. So I simply added this expression to both sides. So I added it over here. So you end up with 0.02 kilograms times 300 meters per second plus 0.02 kilograms times 100 meters per second, and then divide both sides by the 0.5 kilograms, so that all you're left with is V final. And that gives us a very nice 16 meters per second for the final velocity of the block with the rubber bullet. So this is with the bullet that bounced off the wood block. So now let's take a look at the regular bullet. So this problem is a lot like the last one. By the way, I just want to apologize for the lack of talking through it while I'm working on it. I've discovered a small technical issue with the software that I'm using, so I had to pre-write all of it and solve it out. But to show you what happened, so we use our bar chart to make our equation. This plus this plus this is equal to this plus this. So we have our initial momentum here is equal to P final of the bullet plus P final of the wood. Then we plug in our equation for momentum, which is mass times velocity. So the mass of the block, the mass of the bullet times the initial velocity of the bullet is equal to the mass of the bullet times V final plus the mass of the wood times V final. You'll notice that the V final here I didn't specify like I did in the last one where I said V final wood and V final bullet. That is because the two of them are stuck together, if you'll recall, so they actually have the same velocity. So I just put in V final instead of V final wood, V final bullet. Because of this, we were actually able to take it out of the equation, which gives us the expression mass of the bullet plus mass of the wood, so these two times the velocity final. So I was able to factor out V final, take it outside, and have it this way. So we plug in our values and solve for V final. So we'd have 0.02 times 300 is equal to 0.02 plus 0.5 times V final. So V final is equal to 0.02 times 300 over what is effectively 0.52, which gives us a less nice number of 11.53 meters per second. So there you have your solution for the first set of problems, the momentum problem. Come back next time for the torque problems. Enjoy, and see you in the next one.